Fenchurch. I have something very important to tell you. I want to be off in a distant galaxy, fighting aliens.
But we're only 20 years old.
I know, but it's my duty. I have to do this. I'll be gone for about 5 years.
How so quickly?
Well, I'll be traveling in the new spaceship, the Titan 3000, at about 0.992157C in the Earth's reference frame.
That's oddly specific.
Yeah, it is. Well, it's about time for me to go, so I'll meet you at the launching pad. I'll see you in 5 years.
Professor Streetmeister,
Yeah.
I have a problem.
What's wrong?
My husband, he's still not back yet. He left on a spaceship 5 years ago, traveling at 0.992157C, and he should be back by now.
Okay, calm down. We can work on this problem together. Why don't you take a seat? Okay, now, if you look here, the most important thing to review and remember is that time is relative. So this means that when people, objects, or reference frames are traveling at relativistic speeds, such as 0.992157C, the time elapsed between two events will not be the same in both reference frames. So I think what you're asking for is just how do we find the amount of time it takes him to come back to Earth in your reference frame, given that it takes 5 years for him to come back in his reference frame. And to do this, we only need one simple equation, and that time is equal to gamma times the proper time. So the proper time is the time in the reference frame in which both events occur at the same place. In this case, the proper time occurs in your husband's reference frame, because in his reference frame, both events, which are him leaving Earth and him coming back to Earth, both occur at the same place. They both occur at the space station on Earth. So therefore, the proper time is 5 years, like he told you. And gamma is just a variable that we use to transform the proper time so that we can get the time it takes between the two events in your reference frame. So gamma is equal to 1 over the square root of 1 minus the velocity of the reference frame squared over c squared, and c is the speed of light. So we know that the speed of the reference frame is 0.992157c, so it's just a matter of plugging that into the equation for gamma. And when we do that, we get that gamma is equal to 8. And we already know that the proper time is equal to 5 years. So finally, we know that the time it takes in your reference frame for him to come back is equal to 8 times 5 years. So unfortunately, it'll take 40 years for him to come back to Earth in your reference frame. And that means that 40 years will have passed on Earth before he comes back. So it'll be another 35 years before you'll see him again.
Spike, we've intercepted a message. A light beam sent by aliens to your wife. They're trying to lure her to a train station with a bomb.
Oh my goodness! My dear wife, Fenchurch! I have to send her a letter in the message pod to warn her. How fast are we going right now?
0.992157C.
Oh, great! So that means if I send a message at 0.9c, then it'll be going faster than the speed of light, which is faster than the alien's message. So it'll get to her first and warn her.
Yeah.
Yeah!
But wait!
What?
I'm sorry to inform you, Spike, that the speed of light is the universal speed limit in any reference frame. Although our ship is traveling at 0.992157c, and you sent the message pod at 0.9c in our reference frame, it will not be going faster than the speed of light in the Earth's reference frame. Here we have a velocity transformation for one dimension. By plugging in the speed of the message pod at this reference frame here on the spaceship, and the velocity of the Earth's reference frame, which is the opposite of our velocity in their reference frame, we can find that, in fact, the message pod's velocity in the Earth's reference frame will only be 0.999586c, and it will not be faster than the alien's light transmission, which is traveling it. So I'm sorry to inform you that your message will not get to Earth in time to save your wife.
Oh my gosh! Fenchurch! finally home. My dear wife, Fincher, she's probably long dead by now. She didn't get my message in time. Wow. Oh my gosh. What has happened? This world has changed so much. Is that a flying car? I thought it's only been 5 years. Sir, what year is this?
Well, I believe year 3040.
2040? I mean, that should be about 60 years old.
You don't look 60 years old.
I know! What's going on? I'm so confused.